So here we're going to continue to develop this notion of a limit, and our goal here now is to find limits without using a graph. So we're going to start by considering this linear function here that I've graphed for you, and we're going to investigate the relationship between the limit and the function that I gave you. So we want the limit of y as x approaches 2, and x approaches 2 is this x value, and that y value is here. So as we walk along the curve, or the line really, we end up at the same point no matter whether we're coming from the left or the right, and that looks to be y equals 8. So the limit of y as x approaches 2 is 8. And then the question here, is there a way we could have found that limit without the graph? And this should be pretty obvious to you, I think, right? 3 times 2, so 2 is our x value, right? Plus 2 is 8, right? So the answer here is yes. Here's our work. So the way we can do this, find these limits in this simple case, is really familiar to you already. We just plug in that x value, right? So we're just going to plug in the value that we want the function to approach. Now the way this would look in my limit notations, I'd say the limit as x approaches 2 of y equals, well, that equals the limit as x approaches 2 of 3x plus 2. Right, so I've just kind of made a substitution here using this. Well, then that's just equal to, and now I'm not going to write that limit operator anymore as I plug in this 2. I'm just going to say that's equal to 3 times 2 plus 2, which is equal to 8. Right? So make sure you capture this. This is what your work and your good notation should look like. Now, this wouldn't be super useful to us if this was just plugging in x values, because we've known how to do that for years now, right? So let's make it a little bit more complicated. So let's consider these two examples here. We'll start with this first one. So we want the limit as x approaches 0 of f of x, and f of x is this guy. All right, so really we want the limit as x approaches 0 of this function. And notice now, for f of 0, if I try to plug this in, let me just show you this. F of 0, well, that would be 0 times 0 plus 5 over 0. So f of 0, I don't want to say equals here. I want to say it's undefined. F of 0 does not exist because we get 0 on the bottom of our fraction here. Okay, so this is familiar to you. But look what we can do here. We can do a little bit of algebra, and we've done this before. I can cancel out my x's, right? So I'd say that this limit here is equal to the limit as x approaches 0 of x plus 5. So x over x is just 1. So those cancel out, and now look, I can plug in my 0, and the limit is 5. So this would correspond on a graph to a hole in the graph, right? So f is undefined at that point, but the graph would approach y equals 5. We'll look at one more example here. So here we're going to get really clever. So notice I have the same problem, first of all, that if I try to plug in this 2 in the denominator, 2 squared minus 4 is 0, right? So I get 0 in the denominator again. So I can't just make the substitution directly. And notice I can't cancel out x's. Like, this is not allowed because this is now part of a binomial instead of just being an x by itself. So we're going to do something very smart here. So notice my bottom, x squared minus 4, that's called the difference of squares, right? That's factorable. And it factors like this, x minus 2, x plus 2. So that should be familiar to you. You can do this to verify if you want. So you can use a Punnett square and see how this looks, and notice like you'll get my original result. So these are equivalent. We're going to use that to rewrite my function here. So I'm going to say that my original limit is equal to the limit as x approaches 2, and you should rewrite that. It's good notation. The top stays the same, and then the bottom we're going to use this identity here. So we can make the substitution because we know that this is equal to my original denominator. And then look what happens here. So x minus 2 over x minus 2 is 1, right? So those cancel out I'm left with the limit as x approaches 2 of 1 over x plus 2. And then now I can plug this in, right? Because 2 plus 2 is no longer equal to 0. So there's my limit. So what if we can't make a substitution? Well, we can rewrite the function using some algebra skills that we already have. For example, we can cancel terms and fractions. And then we'll learn some other tricks as we go forward with this. But this is powerful, right? Because this allows us now to evaluate what values functions approach without graphing. And it allows us to tackle situations where the function is not defined. So our main idea here is that to evaluate these limits, we plug in the x value, right? And if the function is not defined at the x value, we can try to rewrite the function so that we can evaluate. This is a great time to pause and just make sure you've captured all of the notes on this page, and we're going to move on to another example here in a second. So let's now look at something a little more interesting. So this, remember, is called a piecewise function because it's made up of two different pieces. Here's how it looks graphically, and here is the formula for the function, right? So the reason we get two different pieces is because it's defined differently for x values to the right of -3 versus x values to the left of -3. So the result of that, right, is we get this little jump here at x equals -3. And we already know from our work on limits graphically that this limit does not exist because I approach a y value from the left. I approach 1 for my y value, but from the right I approach -5. So our left and right limits do not exist. So how will we check that analytically? Well, we want to know, right, is the limit as x approaches -3 from the left of f of x, is it equal to the limit as x approaches -3 from the right? And the way we do that is we use these two different formulas here. So notice x less than -3, that's my left-hand piece, right? So this limit, by the way, I'm going to pull a question mark here because we don't know if these are equal or not, or that's what we're checking. So my left-hand limit of f of x is the limit as x approaches -3 of x squared minus 8. And we're checking to see if that's equal to the limit as x approaches -3 of my right-hand piece, which is where x is bigger than -3, which is x minus 2. And then we can substitute, right? So what we get is we get -3 squared minus 8 equals, question mark, -3 minus 2. And this should be pretty clear that this is not equal, right? So I get 9 minus 8 is 1, and then -3 minus 2 is -5. Right? And notice those are the same y values in the graph. And then this is not true, right? So we'd say that the limit as x approaches -3 of f of x does not exist because the left limit and the right limit are not equal to each other. Okay? So the way we tackle these is we need to check both sides if we're interested in, notice these numbers are the same. So if we're interested in where the two curves meet, we need to check the left limit and the right limit to make sure that they are equal, because that's part of our definition of the limit. Okay? So we need to check both sides. And notice it only matters if we're at the boundary of our two pieces, right? Because the limit as x approaches 5, for example, well, that's very clearly 3 from my graph, right? So it only matters at this point, -3, where we have this jump. Okay? So the main idea here is that our definition of the limit still has not changed, right? So the limit only exists if the left-hand limit is equal to the right-hand limit.